Okay, so we're almost done with deriving all these sort of special case results that we're going to be coming back to. And there's one more that we have talked about that we didn't get really a chance to derive, and I'm still not going to formally derive it, but I'm at least going to show you where it comes from. And that is the field of a uniformly charged sphere. So here's a positively charged sphere that has a uniform distribution, uniform charge distribution over its surface. Uniformly charged, or uniformly distributed charge on a sphere. Outside, what's the electric field look like? What do we use for the magnitude of the field outside the sphere? Anybody remember this? You had to use this result in a homework, I think. It looks just like the field of a point charge, right? What's the R? The R goes from where to where? From the center of the sphere, right? So you can sort of treat it like a point charge at the center, and it behaves exactly the same way. Okay, so outside, it's just 1 over 4 pi epsilon 0 q over r squared. Inside, the electric field due to that charged sphere is what? Anybody remember? It's 0, yeah. End up with the electric field due to the sphere. Not necessarily the net electric field, because there may be other charged objects outside that may make electric field at that location. But the field just due to that charged surface gives you 0. How's that work? Well, essentially we do the same thing. We break it up into pieces and add them up. And the pieces that you want to break it up into are actually rings. And let me show you a little program that gives you an idea of how this works. Here's our uniformly charged sphere. I'm going to break it up into rings by slicing it up kind of like latitude lines on the globe from one pole to the other. So there's ring number 1. And since that's kind of hard to see, I'm going to take the surface away and just look at the field due to the ring. Okay. So I have here the field due to one ring, the delta E, and the running total of the total electric field due to all the rings. Here's the next ring. It makes a delta E pointing away from it along the axis, just as rings do, positively charged rings do. The next delta E, and so the green arrow is the delta E, the orange arrow is the running total of the electric field, adding up all the delta E's. And so we get a larger and larger electric field until we get to a point where we're right on the axis, okay, or right on where our observation location is right in the center of the ring. That delta E gives us approximately 0. Go one step past that delta E, or that observation location, and now the electric field due to that ring is going to be pointing in the opposite direction. It's a little bit hard to see here, but that green arrow is pointing now to the right instead of to the left. Keep doing that, and if I zoom in here, we see this delta, this E of the ring getting bigger and bigger in the opposite direction. I keep adding that to my running total, and that running total keeps getting smaller and smaller and smaller because I keep adding up more and more electric fields pointing in the opposite direction. When I finally reach the other side of the sphere, it actually does add up to be equal to 0. And you can do it analytically, and it's worked out in the end of the chapter if you want to actually take a look at it. We won't go through it. But it actually does really, really work out to be 0 inside. Okay? Next time we will start something new.